Next topic is Hooke's law. This was a law given by Hooke between describing the relation between stress and strain. He showed that the two are directly connected to each other with an experiment. He applied the force on a body and studied the amount of strain produced inside the body, the extension produced inside the body, and then he related both of them. He came to know that stress was directly proportional to strain. When we increase the amount of force on the object, the strain, that means the change in configuration, also increased. And then it was concluded that the two are directly proportional. We'll note down the statement first. It states that the extension produced in the wire is directly proportional to the load applied within elastic limit. Okay, extension produced is directly proportional to the load applied. Here the extension produced is related to strain and the load applied is connected to stress, and they both are considered to be directly proportional, and that too obviously within the elastic limit, after which they do not have a specific relation between them. This follows within the elastic limit of the material. It can be expressed as stress proportional to strain, and when we removed the proportionality, we got a constant here, that is E into strain. This E here is a proportionality constant. This was termed as modulus of elasticity. Modulus of elasticity. It depends upon the material of the body. Material of the body. Every material has its fixed predefined modulus of elasticity, under which the stress and strain of that particular material are related. इसमें अगर अपन इनके बीच में ग्राफिकल रिलेशन प्रेजेंट करते हैं, so being directly proportional, we know the expected outcome, that there is supposed to be a straight line.
सर स्लोप होगा 1 का स्लोप होगा इंक्लिनेशन 45 का होगा.
So if we take extension here on y-axis and the load applied here on the x-axis, we got to have a straight line between the two as they are directly proportional. Next title is modulus of elasticity. It is also called as coefficient of elasticity, denoted in general by E. We'll have a basic definition for this, a statement. It is defined as the ratio. We are writing this statement on the basis of Hooke's law itself. Ratio of the stress to the corresponding strain produced within the elastic limit. Within the elastic limit. Now, modulus of elasticity are broadly classified into three categories. They are classified into three categories. One is Young's modulus of elasticity, denoted by capital Y. Bulk modulus of elasticity, denoted by K. Modulus of rigidity, denoted by eta. This is also called shear modulus of rigidity, or simply shear modulus, eta. So we need to discuss the unit of the modulus of elasticity of all these types, all these kinds. All the modulus of elasticity, whether it is Young's bulk or modulus of rigidity, they all are the ratio of stress to strain. They all are the ratio of stress to strain, as the definition also clearly indicating. The unit of stress is Newton per meter square and strain is unitless quantity. And therefore, all the modulus of elasticity, they have the same unit as that of stress, that is Newton per meter square, or we can say pascals. All of them have the same unit, pascals, or we can say Newton per meter square, and accordingly they all have the same dimensions, that is ml minus 1 t minus 2. Young's modulus of elasticity. Young's modulus is basically involved at those times when we are considering the extension or compression in length of the wire. Length of something. If length of something is involved in the form of strain, then we go for the Young's modulus part. We just need to remember which kind of stress and strain are involved in that particular modulus which is governing it. So we'll first write the statement for Young's modulus. It is the ratio of the statement will cover that particular type of stress and strain. It is the ratio of normal stress, I'm highlighting the two things, normal stress to the longitudinal, that means that one related to length, longitudinal strain, longitudinal strain within the elastic limit, within the elastic limit. So the expression clearly connects as y equals to normal stress, that means the first one that we studied, the perpendicular category, normal stress upon longitudinal, the one involving the change in length, longitudinal strain. Using the formula of the above two, normal stress is force per unit area, whereas longitudinal strain we studied already, delta L by L, change in length upon original length. So the final expression that we get for Young's modulus is FL upon A delta L, where A is the cross section area, which can further be written as pi r square, cross section area of the wire. This is the final expression for Young's modulus, on which we are going to have the numerical section. Let's have a sample question. The question says a steel wire of length 4 meter and diameter 5 mm is stretched by 5 kg weight. Find the increase in its length if the Young's modulus of the wire is 2.4 into 10 raised to the power 12 dyne per centimeter square. In the variable part, we'll take length as 4 meters to be converted into respective units. Diameter से आपने radius हमने calculate कर लिया, which will be 5/2, that is 2.5 mm right now. And force was an important part here, which is given in kg weight. Kg weight when multiplied by 9.8 will convert it into newtons, or even if when multiplied by 980, we can get the answer in dynes. And similarly, we already have the value of y in 2.4 10 to the power 12 dyne, that is in CGS. We could have carried out the question in CGS, that too is also okay. And if we carried out in the form of SI units, that too is also okay. Any one of them can be followed. This will be 0.25 cm. And the calculations now can be done directly by using the given expression. All the values can be substituted directly into the formula. Next coming up is bulk modulus. representing by K. We'll have the statement again in which we are going to focus on the type of stress and strain involved. It is the ratio of normal stress, again similar to the Young's one, normal stress to the, now the previous one was involving longitudinal strain, and this here involves volumetric strain that we had studied in types of strains, volumetric strain. And yes, that too within the elastic limits, within the elastic limits of the material. Okay, if we talk about the expression, it will be K is equals to normal stress upon volumetric strain. Now, if we are trying to compress a body, we need to apply some force over that particular area. So the normal stress is again perpendicularly exerting force on the area, that is F by A again. And the change in volume, as the volume is decreasing, we are talking about the compression, that will be minus delta V upon V. Negative change in volume, that means the volume is compressing, divided by the actual volume. So here K is equals to FV upon minus A delta V, minus A delta V. And since we are talking about a bulk, since we are going for compression, we can have gas here also, gas involved. So instead of writing F upon A, we could have also involved pressure directly. So that will be pressure into volume upon minus delta V, minus delta V. So these are the various forms in which we can represent the bulk modulus. This is in context. We can consider that we have a spherical solid body which already has a volume V, and we had applied some external force over it, and we have compressed this body by delta V volume. So the volume remaining with us is V minus delta V. So for such kind of compression, we got to have this bulk modulus expression. Okay. In terms of bulk modulus, since we are undergoing compression for a gas or a liquid, we have a property that can be calculated by using the bulk modulus, which is called as compressibility. Compressibility can be expressed in terms of the bulk modulus. Here compressibility is denoted by C, and it is simply the reciprocal or the inverse of bulk modulus. The inverse of bulk modulus gives us the measure of compressibility of that material.
Hmm.
S, SI unit can be accordingly set, which will be just the inverse of the bulk modulus, that is Newton inverse meter square.